Welcome back. So there's typically one type of asteroid. Typically there's one type of comet. However, meteoroids that eventually hit the ground, there's actually a few different types of those. And it's based on that consistency. It's based on when an asteroid breaks up into smaller pieces, into meteoroid-sized pieces, where do those pieces come from? The core, kind of the outer crust, or that in-between layer? So, we have stony meteorites, we have iron meteorites, and then in between the two we have stony iron meteorites. Go figure. So stony meteorites, a type of stony meteorite is called a chondrite. It's the most common type of meteorite found on Earth. It comes from the outer layer of an asteroid that's broken up. Typically, it will have a black crust. It's slightly magnetic. So all kind of, I don't know, most meteorites are magnetic, not the ones from the moon or Mars. All meteorites that come from asteroids, broken up asteroids, are magnetic. But just because something is magnetic doesn't mean it's a meteorite. For example, there's a black rock, igneous rock called basalt. It's also kind of magnetic. So very commonly I get people asking, oh, is this a meteorite? It's black and it's magnetic. No. Just because it's magnetic doesn't mean it's a meteorite. But if it's a meteorite, it needs to be magnetic for the most part. So they're slightly magnetic. In that black crust, it kind of has cracks on the outside. This is from, essentially, it's burning up and melting as this meteoroid is going through the atmosphere as a meteor. So stony meteorites, specifically chondrites, may contain little grains of rock called chondrules. These are the very beginnings of the solar system. And some of these chondrules even predate the Earth, and that's really what gives the age to the solar system. It was just a little bit older than 4.54 billion years. So if we were to cut one of these stony meteorites in half and look at it from the side, it's made up of all these little pieces of rocks and minerals. That's the early material of the Earth. That's the baby, or excuse me, let me take that back. That's the early material of the solar system. That's the baby picture of the solar system. As the solar system was forming, as there was just a bunch of swirling gas and dust out there in space, and this material began to come together under the force of gravity, it started to form initially these little pieces of minerals and rocks. And those little pieces of mineral and rocks got squished together, and more stuff got squished together. That's what formed the planets. That's what formed our star, the sun. So those beginnings, those very littlest pieces that started to come together, those are chondrules. And that's what makes up these meteorites, which is typically coming from the crust of broken up asteroids. So that's the solar system's kind of baby picture, essentially. It's the DNA of the solar system. Then we have iron meteorites. They're 90 to 95% iron. The rest is nickel and a mix of other elements, but mostly metal. This is coming from the core of the asteroid. It's very heavy, very dense. It's mostly heavy iron. Strongly magnetic. It's almost all iron. Very strongly magnetic. A cool thing with iron meteorites is that the iron-nickel mixture, known as an alloy in metals, it can actually grow crystalline patterns. And this only happens if iron and nickel are cooling and forming in a zero-gravity environment, like out in space. Here on Earth, if we have molten iron and we're cooling it off and it cools to a solid, it's not going to form this crystalline pattern that we sometimes see when we cut open and kind of polish the inside of iron meteorites. This only happens outside of the realm of gravity, so out in space. And this texture is called Widmanstätten texture, or Widmanstätten texture. This cool, like, triangulated kind of pattern. Again, that only happens when iron can cool and form and crystallize, but there's no gravity. Under gravity, it's not going to form this. So this shows that this big chunk of metal and iron formed somewhere where there is no gravity. So again, this stuff is coming from the core of broken up asteroids. And then in between the two areas of asteroid, the crust and the core, that's where stony iron meteorites come from. An example of that type of meteorite is called a palisite. It's the least abundant of all the known meteorites that we found on Earth. Only makes up about 2%. Most are stony meteorites. There's a good amount of iron meteorites, very little stony iron meteorites. It's equal parts metal, iron, nickel, and equal parts the minerals and stones from the crust. Because again, it's coming from that boundary between where the crust of the asteroid is and that metal core of the asteroid is. It is also slightly magnetic. Again, if it's a meteorite coming from an asteroid, it's going to be magnetic. What's really cool about these meteorites, you can slice them, and if you can get thin enough slices and polish it up, you get this really cool kind of metal matrix, and then with minerals kind of embedded into it. And if you slice it thin enough, light can come through these things and it just makes a spectacular display. Since these are the rarest type of asteroid-based meteorite, they're kind of expensive. Not as expensive as a meteorite from the moon or Mars. Those are very, very expensive because they're very rare. But as far as the more common forms of meteorite, in this case the stony iron one, it can be kind of expensive. Now, another common thing that some people mistake for a meteorite, but that's truly not, and you can tell right away because they're not magnetic, is some of the material that gets ejected out from an impact site. So let's say a large meteorite or even an asteroid strikes the ground. What's going to happen? Some of that material is going to melt. Some of the Earth's material, because of the heat and pressure, is going to melt and get kicked out into the atmosphere and then fall back down to the surface. Now that material, because it's melted, it's essentially magma or lava in this case, and then it cools very, very rapidly, it kind of forms a glass. And this ejected glass material is called a tektite. So again, this is a glassy object formed as ejected molten debris in meteorite impacts or asteroid impacts, and can be scattered widely throughout the impact zone, the impact site, which is kind of cut off here. My apologies. So all of this is kind of glassy material. And what's interesting is the shape that we find the tektites will actually help us zero in on where maybe the impact site is. So if we are finding tektites that are kind of like a peanut shaped, and then we kind of find some more, but they're more kind of like a dome shaped, then we're actually getting away from the actual crater. So if we could then go the other way, we have a peanut shape, and then we find more of just an oval or roundish blob shape, we're actually heading in the direction of the impact crater itself. So there's a lot of stuff that's related to an impact site that's not the space material itself. These tektites, which look very spacey, look very meteorite-y, are definitely not. Cool stuff, and in some cases can be different colors and kind of rare because of whatever the material the asteroid or meteorite is slamming into will form. Different minerals, different rocks will form this different tektite glass. But they can, again, kind of help us zero in on where maybe the impact site is. So it's kind of like doing a little forensic investigation. All right, so let's pause there. That's just kind of some a good review, or just introduction, I should say, to stuff that hits the Earth. And now we're going to start talking about, well, what threat does that stuff actually pose? Now we're going to get into the hazard and disaster of it. I'll see you back here in just a second.